This conference will now be recorded.
Perfect, Tom. Yeah, it's all clear. Thanks.
Okay, thank you. Well, thanks, folks, and thanks for the introduction, Russell. It saves me having to read all that stuff that's there on the left-hand side of the screen. The introduction to tonight's talk, track design, the basics. If you're looking for an in-depth introduction to track design, it won't be here tonight. We're going to just look at the basic stuff, the things that you might know, or that you should know, depending on your job, and things that you might like to know. I'm going to discuss things tonight like how railway tracks were developed from simple wagonways to the modern track forms that we know and love, the types of geometry elements we use in track alignment and how these are connected together, how to perform simple alignment, I stress simple alignment calculations, nothing too daunting in there, and I'll discuss the need to have design limits to provide safe and comfortable track systems, and how to use those design limits and alignment geometry to calculate the safe speed of trains. So we've got kind of 5 topics: brief history, a bit about track form. We're going to talk about what track's made from, track function, what does it do, track design basics, how you create track design and what limits are applied to it. And then I think called the design workshop. Don't get scared by that. It's just some worked examples I'll show you of design calculations, and maybe if we've got time, you'll have a chance to try them out yourself. The information in the slides is all done in a set of notes, and this is going to be made available afterwards in a notes presentation. So if you miss any of the step-by-steps in the calculations, then you'll have those at your fingertips should you ever need to refer to them. Okay, a very brief history of track then. So answer the question, where did it come from? Well, until the middle of the 19th century, all wheel transport involved wheels with rigid rims. Rubber tyres with air inside them, pneumatics, hadn't been invented yet. And on the regularly used routes, most road surfaces and the foundations for them were very quickly damaged by the heavier wagons with rigid wheels, creating ruts on the paving or road surface. Early problem solvers found that a more durable hauling route or wagon way could be maintained by providing a surface of stone slabs or wooden balks, timber rails if you will, which spread the load over a larger area and prevented the ruts from forming. And that little Fred Flintstone mobile there was a genuine thing that actually did run. In Britain, different types of early wagonway tracks were tested as early as the 16th century, so 1500 something, and these generally followed the Roman roads in the UK. Typical construction involved laying long parallel strips, rails of timber, for the horse-drawn carts to travel along more easily, and these railed ways created less rutting of the road surfaces. You see the terminology start to develop there? However, by the middle of the 18th century, industrialization was forcing mine owners, principally, to reduce their maintenance costs of these railed ways, and some added wrought iron plates on top of the wooden rails to extend the life of the timber. Made sense to do that. Wrought iron was available. The addition of these metal plates meant that even heavier loads could be hauled out in the mines with much less downtime due to repair or renewal of the long timber rails. Even so, the days of long wooden rails became numbered when a guy called Benjamin Outram, and that's not him in that picture, I think that's a fellow called Gash McRae. I could be wrong, but Benjamin Outram constructed a mile-long wagonway with L-shaped cast iron angle rails, he called them, and you can see them in the picture if the wee laser pointer will work. See the angle there? Angle L. So that back angle there is what's keeping the wagon on that track. And that idea, simple as it was, began to take off. However, before very much longer, those angle rails became obsolete, because about 7 years after they were invented, a modest Devonshire engineer called William Jessup began to manufacture cast iron rails without the guiding ledges. How did that work? Well, Jessup's brainwave idea was to transfer the ledges from the rails onto the wheels of the cart. So he took the edge there and he stuck it round the rim of the wheel. A brilliant idea. And so the earlier angle rails were replaced with a thing called raised edge rails, which were lifted higher above the ground to accommodate the use of the new flanged wheels. And there's a little picture of a wheel and some flanges on it. The grey areas there, the flanges on the insides, and the wheel treads are coned slightly. An axle through the middle, sitting on top of rails, sitting on the sleeper on a bit straight track. So the modern railway was therefore now invented with flanged wheels sitting on top of the rails. But the wheel flanges aren't not intended actually, to come in contact with the rails and provide guidance. They do provide a bit, but they're a safety feature, something of last resort, which prevent the wheels becoming derailed. The vehicle guidance is provided by the shape of the track, obviously, and by the cone shape of the wheel tyre and the railhead being inclined towards the track centre. And I know it's not in that diagram, but I couldn't find one that was. On straight track, the sideways movement of the axle is continually being corrected by the speed of the wheel, since both wheels are rotating at the same speed, and the same effect happens on the curves. It tends to move the wheel back to a central position on the rails, and this is called equivalent conicity. The edge rails needed a much closer match between the rail spacing and the width of the wheel sets were also important that they matched up with the width of the rails. And the importance of retaining the space between the rails, or the track gauge, became quite apparent to the early guys that were inventing this stuff. If the gauge was too wide, the carts simply fell off the tracks. If the gauge was too narrow, the wheels jammed, or the flanges rode up over the edge of the wheel and then fell off. And that's pretty much the same as we have today then. It's important to note at this stage the spacing between the rails was largely determined by the width of the local carts, and nothing was standardised. So you made your little system on your mind somewhere to suit whatever carts you had to hand. Not strictly the width of a horse's back end, but you could say that that is partly true. And there's the very horse. The term permanent way was first used when the early railways were being constructed. To enable the excavation and transport of the huge volumes of material that were involved, a temporary railway, occasionally a narrower gauge, was created. The permanent railway, or layout of running lines, was then constructed once the bulk earthworks were completed. And we still use this method today in certain circumstances. We use the track next to the track we're trying to renew or build as a method of transporting the materials. Richard Trevithick is credited as a designer and builder of the first steam loco to run on rails. In 1804, Trevithick had developed the technology that was originally used to pump water out of those mines. But the very first passenger-carrying public railways used horse-drawn carriages on cast-iron rails. The first fare-paying service was opened in Wales in 1807 by the Oystermouth Railway, later known as the Swansea and Mumbles Railway, and that's a picture of it. Obviously the driver there, Speedy Walker, is trying to get the horse to pull that big heavy cart. And the horse is thinking, I ain't moving until one of you guys gets off. It's hard to believe that single horse could pull that thing, but there you go. As steam power developed and as haul loads increased, the use of brittle cast iron rails became more and more of a problem for those early railways. Broken rails were a fairly common occurrence, and in fact were a fairly common occurrence when I started in the railways in 1974. Maybe that's a bit exaggeration. The major issue was finally overcome in 1820 when a guy called John Birkinshaw introduced stronger rails using rolled wrought iron sections. Even so, at that time, track gauge dimension was still uncertain. We didn't have a standard gauge. George Stephenson was still constructing his Stockton and Darlington Railway, which in 1825 became the world's first public railway to use steam locos. To save costs, Stephenson recovered material from an earlier railway developed that he'd been involved in at Hetton Colliery, and it made sense that the wagons used on his finished railways were built to the same dimensions, which incidentally had a track gauge of 4'8" or 1422 millimeters, not 1435 that we use today. Two railways with the same gauge? Surely just a novelty. So for the first half of the 19th century, 1800 to about 1845, narrower and broader gauges than Stephenson's were widely used. Narrow gauges were good for the steep routes in the Welsh hills, and the broad gauges were better for the faster plains of southwest England. And the most celebrated example of broad gauge was Brunel's choice for the Great Western Railway, and he managed to persuade the directors to adopt 7 feet 0 1/4 inches, 2140 millimetres, as the track gauge. However, if you think about it, narrower gauges were quite economical to construct. Big 7-foot gauges needed a lot of construction. Structures were narrower with narrower gauges, and the narrower gauges became increasingly adopted for new lines. So Brunel was kind of persevering with 7 foot, but he was in a shrinking pool. As travel horizons broadened and longer journeys became possible, the technological and economic implications of having different gauges forced a decision on standardising the gauge for all railways, because it became obvious in the UK that if you didn't have the same gauge, you couldn't go very far, or only as far as the next change of gauge. So in 1845, a Royal Commission decided in favour of Stephenson's gauge, which by that time had become 1435. It took until 1892, though, for the last broad gauge in Britain to be finally abandoned. Stephenson's gauge was slightly developed from his original 4 foot 8 by adding another ½ inch for comfort and to reduce wear in the curves. The dimension between the edge faces was 4 foot 8 1/2, 1435, as I said, and this was eventually accepted as being the standard gauge for track. Having adopted standard gauge at 1435 and as the industrial technology leader at the time, the UK then influenced gauge selection on the majority of the developing world. Only influence, didn't persuade fully. And that takes us to track form. Mark Taylor points out that cart was the Edinburgh to Biggar bus. Okay, well, let's go and look at what's it made from, this thing called track. So when the Stockton and Darlington Railway opened for business in 1825, first passenger steam-drawn local railway, it was constructed using 15-foot long T-shaped rails supported in chairs, because that's what they looked like, on top of stone sleeper blocks set at about 3-foot spacings. The rails weighed 28 pounds per yard, not very heavy at all. They were 2 1/4 inches wide and 2 inches deep at the chairs, and, as you can just about see in that picture, they were kind of bellied out in the middle, and they called that a fish belly. They opened out to 3 1/4 inches at the middle. That helped support the bending. Stephenson used a similar form of track construction on the Liverpool and Manchester Railway, but he made them with stronger rails, up to 35 pounds a yard, then 50 pounds a yard, then eventually 75 pounds a yard, because he was wrestling with this broken rail issue. As linear track mileage grew and the weight and wagons and engines increased, it became impractical and uneconomic to continue using stone blocks as rail supports, mainly because that fixing did actually have a very good gauge retention. The blocks could move, the gauge could widen, and the train would fall down between the rails. A different form of support was needed that would both bear the load and hold the gauge. Brunel, meantime, sought he'd solved it. His broad gauge railways had a novel concept of 30-foot long rails supported on longitudinal timbers. So a longitudinal timber is one that goes along that way, just underneath the rail. And he had transverse timber spacers set at 15-foot intervals, held down by timber beechwood piles, all very robust and all good at holding gauge. This was all supported on stone ballast, which allowed good drainage and enabled realignment to be done. And yes, very little has changed. Does anybody recognise the back of Graham Wishart? That's him there with his finger in the air. We still use the three main components which made up the early track forms: crushed rock, wooden sleepers, metal rails, and it can be said that the present day track has developed little since the original construction concept. Of course, these days we use longer, 60-foot minimum, 18288, and stronger steel rails, but these are still connected by mechanical bolted fish plate joints, and railways are often supported on wooden sleepers on ballast. And these little things in here, there, another one over there just beside of Wishart's foot. New mouse, can't do a thing with it. There. That's a fish plate. That's a fish plate. Mechanical joint, you can just about see that one there. So this is all connected together mechanically. Why do we do that? Why did we change it? Well, in many locations, large-scale changes of track form are not very cost-effective, and we simply carry on maintaining and replacing tracks which have been inherited from the days of steam as a like-for-like renewal. And that little picture is Glasgow Central Station, for those of you that recognise it, and that wasn't taken that long ago, although maybe it was. Anyway, it's the same today as it was before. High-speed lines tend to use a more modern track construction to cope with the higher speeds and significant tonnages we carry. They use continuously welded rail and either concrete, steel, plastic, FFU, that's fibre reinforced foamed urethane, as alternatives to timber sleepers. The steel sleepers are much lighter than the concrete ones, 84 kilograms versus 284 kilograms, but both the components provide adequate resistance to track movement, albeit in different ways. Steel sleepers have elongated ends, which oppose the movement, and the concrete sleepers rely mainly on the frictional resistance between the underside of the sleeper and the ballast. Ballasted track forms are still the norm, as they were in the early days of railways. Why is that? Well, ballast as a track support can be fairly easily removed, it can be replaced, and it allows the track geometry to be rearranged to suit evolving traffic patterns and higher speeds. In the UK, Network Rail engages in a programme of track renewal in each region, which generally involves a like-for-like replacement, with worn-out tracks being replaced by modern track forms. You use crushed rock ballast for track support, and that's still preferred due to its low cost. It's got excellent drainage properties, and that's vital for the cyclic loading and unloading wears the ballast grains down. That creates fines, which then block the drainage pathways, and dirty ballast needs to be cleaned or replaced. So ballasted track forms are still the norm. In the UK, during renewal works, the opportunity can be taken to improve, enhance or rationalise track layouts to meet the future aspirations, and that's where track design comes in. You wouldn't dream of going out to renew a piece of track and just eyeing it in these days, or setting it out using wooden pegs and string. You would have a full topographical survey, you would have some track designer somewhere design the track, and then that would go out to construction, and the guys would use total stations and the like to set it out using coordinates. During track renewal works, we can rationalise those track layouts to meet the demands of the current railway and the future aspirations. The demand for rail services continues to grow, even though we're in a little bit of a hiatus at the moment. And since the life of the track asset is roughly 60 years, the future-ready railway needs to be constructed now. So the railways we're running on today are 50 years old typically, and some of them are even older than that. There's other track forms around. Concrete slab track is preferred in tunnels and on the high speed lines. So for high speed trains, speeds above 140 miles an hour, concrete slab track is the preferred track form. It provides better resistance to the forces involved at higher speeds. It requires less maintenance, and it doesn't have those nasty loose particles of 50 mil single size granite aggregate roaming around in the aerodynamic flow at the wheel rail level. It's expensive to install, but it does provide you with good track alignment control. And despite the high initial cost of construction and the disruption it causes, concrete cast in situ slab tracks and the modular precast concrete slab track are becoming more popular, and at certain locations it's really the only solution that can be installed to achieve high track fixity and clearances to electrified trains. Think Queen Street Tunnel. However, you need to maintain a smooth transition between the stiffness of the concrete slabs and the resilience of the ballasted track. And you need to make sure that that is controlled, especially if the speeds are high. Special devices can be installed, and that's a picture of a thing called VTrans, which has got a tapering beam, steel beam, supporting these steel plates on which the sleepers are going to be placed. And that will reduce the stiffness from the concrete out to the ballasted track. On to track function already. We're fairly whizzing through it. Okay, track function, what does it do? The only thing we do in track is fulfill a service need between A and B. The fundamental requirement for any railway track is demand, normally confirmed by a feasibility study these days. I don't know how the Victorians managed to figure it out. But these studies today establish the need for a rail service by looking at the forces that drive demand, be it for products, moving freight from A to B, or passengers from A to B. And whenever there's a financial case to support that, the proposal to provide rail services is normally made, as opposed to other forms of transport, because it's economical to do so. Any railway track must be able to meet the demands of current and expected future demand. We spend a lot of effort these days building the railways today that's going to meet the forecast demand in 2043, for example. Changes are costly to introduce once rail services and the track layout are established. So you need to think about the future, plan ahead, think where the demand's going to come from, and try and create a layout that's at least going to meet that demand or has future proofing to provide that demand. So if you're looking at electrifying the railway, single line railway between, say, Barrhead and Kilmarnock, you need to make sure that if you're going to electrify it as a single line today, you've got enough space to electrify it as a double track tomorrow, should the service demand be predicted to be such that it requires a double track railway. It does a little bit more than that, the track. It safely guides rail vehicles, that's a kind of given. And the other important thing it transfers the loads evenly down to the subgrade, that's down at the formation level. And there's a little graphic there about the surface pressure on the track. So achieving the optimum formation stiffness, which is able to effectively spread the loads, is an important factor in the design of a track form. It provides the basis for having good track quality. That reduces maintenance interventions and avoids premature renewal. Nothing too rocket science about this. Can't be too stiff, not too soft. Too stiff and the rails will corrugate. Too soft and you won't be able to keep a top on it and it'll feel pretty ordinary for the poor passengers that are travelling along it. In fact, severe track geometry problems often have formations with poor stiffness characteristics as a main contributory factor. The formation below the track needs a crossfall, like a road camber, to allow water to run off to the drainage system or to the embankment slopes or longitudinally along the track sides. In cuttings, the ingress of water, as runoff from external surfaces or from higher water tables, is often intercepted before it reaches track level. And in fact, track drainage systems quite often are not actually draining the track. They're preventing the water that's presented to the track from a third party, farmer's field, for example, from getting into the track and making it waterlogged. So transferring loads evenly down the subgrade of formation is important, and those little pyramids are the effective way that that's done. All the formation elements must combine effectively, and the support layers must be compacted uniformly to achieve a stiffness layer which can transfer the heavy loads without permanent deformation. The required levels of stiffness or of bearing capacity increase depending on the anticipated speed and tonnage from the tracks above. For new tracks, the typical stiffness values are 60 kilonewtons per millimetre at the sleeper end for speeds up to 100 miles an hour and 100 newtons per millimetre at the sleeper end for higher speeds. I can hear some of you shuddering at this picture. This is not a good picture. Track form needs to enable drainage and avoid flooding. Now that picture, which is brand new sleepers being placed on, let's call it fairly ordinary ballasted subgrade, isn't going to achieve drainage and prevent flooding. That's just a little recipe for disaster. The effective control of water is essentially part of the safe and economic management of any railway infrastructure. Water has an important and dominant role in most of the degradation mechanisms that affect track infrastructure, such as the scour of flood defences on bridges, and it affects the track by having a long-term softening of material that form the track support system. The cyclic loading is an issue. So as the wheels load the sleeper transfers that to the subgrade. Every axle on every train has that pumping up and down effect. Many track bed problems begin where track drainage is not operating effectively, or where changes in the position of the water table have created the need for additional drains. Ineffective track drainage can result in temporary speed restrictions or temporary closures of the line, increased maintenance costs, and poor drainage can even disrupt signalling equipment. Track circuits can fail if the formation is too wet. And when water is not captured and directed to a suitable outfall, that saturation of the ballast layer accelerates particle abrasion, reduces the stiffness of the track bed, which results in horizontal and vertical alignment faults that affect ride quality. So it's absolutely important you keep the track clean and dry. The other thing track has to allow replacement of worn or defective components. None of this is very rocket science, but if you have a system that doesn't allow you to do quick and easy repairs, it can be a bit of a problem. So the different components which make up the track subsystem, the ballast, the sleepers, the rails, the small components, rail fastenings, they all degrade at different rates, and it's therefore important to be able to renew those individual parts as necessary without the need for a wholesale renewal. So when your rails wear, you want to be able to change the rails without changing the ballast bed. When the ballast's dirty, you want to be able to clean the ballast without changing the rails of the sleepers, and so on. Effective track systems allow individual components to be replaced as they reach the end of their service life. For example, and depending on service conditions, ballast will typically last between 15 and 20 years, rails may last up to 50 years, and sleepers have a typical life of 60 years. Sustainable track form renewal policies can be implemented. Ballast can be screened to remove fines and small particles, and the ballast layer supplemented with new aggregate. What you take out can be cleaned and recycled again, and worn rail from higher speed lines can be removed and cascaded to lines with lower speeds or lower tonnage. We just have to think sustainably about that and realise that it will cost money, but it is actually sustainable. The bit you've all been waiting for, track design. Track design is the art of combining track geometry elements to provide safe and comfortable track alignments and track layouts, which meet the needs of the operator and the service users. In this next section, we'll explore the fundamentals, not get too hung up on stuff. It's an art, and we'll discuss the limits which govern the art and the process. Units I'll use are metric and imperial. I'll talk seamlessly about meters, kilometers an hour, meters per second, but they'll mainly be in metric because, well, it's easier. The symbols I use are not universal. The terminology is deliberately kept as simple as possible. Please don't let anybody get precious if I talk about EA instead of E, or I say E instead of EA, or D instead of RGD. Here we go. Okay, how do we create track designs? Track designs are dead simple. There's only 3 geometric elements: curves, spirals, and straights. In fact, there's only one: curves, because spirals are curves and straights are just curves of infinite radius. So curves with a single radius are called simple curves, and those with more than one radius are called compound curves. So you can be traveling on a curve of one radius, then take a spiral curve and go to a curve of another radius without encountering a straight piece of track. So there's some formula that allow us to calculate the radius of curves, and that's on the screen there. R equals c squared divided by 8v in meters. All units must be the same. That's a note. So in the little diagram there of the semicircle, we've got a radius r, we've got c, we've got points 1, 2, and 3, and a bit in the middle that measures a thing called v. So r is the radius of the curve, c is the length of the chord between 2 points, i.e. from point 1 to point 3 in the diagram, and v is the offset measured at the midpoint, that's to point 2. That's measured at right angles from the middle of the chord to the second point. Obviously, in the railway, where we're using large radius curves, then the v versine is quite small. Simple tools that all you need to measure curve radius. All you need is a tape measure, a wire, and a ruler. And the wire can be a piece of string as long as you can stretch it tight enough. My own wire of choice is 40mm nylon monofilament fishing wire, although it can cut the hands when it's cold and wet. And calculating the radius is also simple enough. And these days, phones with calculators make it even easier. So here's a little worked example. R equals c squared over 8v. So when c is 10 and v is 23, what's r? So r is something divided by something, and that will give you an answer. So those of you that get the calculator can quickly work that out. That'll save you the bother and say, there you go. 10 squared divided by 8 times 0.23. Remember, keep all units the same. So I'm keeping it in meters. So C is 10 meters and V is 0.023 meters. The radius of that curve on a 10-meter chord is 543.478 meters. And that, in railway terms, is quite a tight curve. Okay, so when using C equals 20, V equals 0.05 meters, here it is again. You square the 20, you get 400. 8 times the 0.05 is 0.40. And even I can do that in my head and figure out that that's a 1,000-meter radius. Nothing too difficult so far. Good. There's an alternative way using a special relationship between the chord length and the versine. So if you want to know R and you're using a 10-meter chord, then R is 12,500 divided by V. So for C equals 10 and V equals 23, we get 12,500 divided by 23. Same answer, 543.478. But if you use a 20-meter chord, the equation is R equals 50,000, not 12,500, divided by V. And you can see there, because I've doubled the chord, I've multiplied that magic number by 4. Okay, spirals. That's a lovely spiral, isn't it? I like that. Spiral curves provide a controlled gradual change in curvature between 2 curves of a different radii, or between a curve and a straight, or between 2 curves of a different hand. A Euler, sometimes called a clothoid spiral, directly reverses about a point where the radius is calculated as infinity, In other words, where the versine reading is 0 millimeters and the track is momentarily there, straight. So if you were to measure the versine at that point by stretching a chord across there, you would get 0 millimeters as the offset. It would be a straight. And here's an example of a direct reverse. There are brownie points for anybody who could put that station into context and tell me which station it is. Only brownie points. So in the chat, you can type, this station is X. Well, I know where it is, by the way, just in case you thought. And the question is, what benefits might there be by putting a station on a direct reverse? Well, there are some benefits. One is in train preparation. And the answer is that train dispatch is much easier since the whole train can be viewed from a single point, and passengers can be confirmed as being on board or about to join. So train dispatch is made a bit easier, but there's always a downside, and the disbenefit of that reverse curve at that station platform is in the maintenance of it. Track maintenance activity must be closely controlled to ensure that the clearances between the platform and the trains are neither too small nor too large at the same time as you're having a uniformly changing curvature, which then reverses and goes back to the other hand, left to right and vice versa. Mark Taylor, you're wrong. And if you look at how we could draw or chart the radius, there's a little table there with chainage going from 1,000 to 1,200 meters. The radius starting at 2,000 and finishing at 1,725 on the different hand. And the versine goes from plus 25 to minus 29. If you chart it as chainage versus radius, you get that weird sawtooth in the top picture. And I always find it more useful to use it as chainage versus versine, and then you can see the smooth transition between the two elements from the 2,000 radius curve to the 1,725 meter radius curve as it goes through 0, and you can identify the point of direct reverse. Oh, we're getting a bit animated now. So, horizontal plan geometry. It relies on accurate survey and control. Poor survey never creates good alignment. And the individual geometry elements and how they're controlled and combined are limited by rules and standards to ensure safety and comfort. Track geometry underpins track form and function. It provides safety for all rail traffic by controlling those physical forces. To fully balance centrifugal forces, that's the outward throw as you go around a curve at speed, the outer rail is raised above the inner rail to create the equilibrium cant, or EQ, when the forces generated by speed around the curve are 0. So let me explain what I just said there. So when you're turning on that vehicle there, going around that curve, you will be thrown by centrifugal force this way. If you super elevate or raise this rail above that rail by the right amount, you can have no forces, neither inwards nor outwards, and you're said to be traveling around that speed, that curve in equilibrium. Now, that equilibrium is only good for a single speed, but we can calculate it. How do we do that? We use an equation. The equation is EQ equals 11.82 times the speed squared, if it's in kilometers per hour, divided by the radius in meters. But only when the track gauge is 1432 and only when S is 1502. Now S in that picture is the track gauge of 1432 plus half of the rail head width, or one full rail head width. So if the rail head width is typically 70 millimeters, 1432 and 70 is 1502, and that's what we use as S. So if you've got standard gauge track 1432, your equation is 11.82 times the speed squared divided by the radius. Oh, hang on a minute. Where does the 11.82 magic number come from? And not a lot of people know this, which I find surprising, but there you go. Let me explain. We use a formula. The Euronorm 13803-1 describes the variables in that formula and derives the constant C, that's the magic number 11.82, and that is the distance between the wheel contact points, S, divided by the speed conversion factor, usually kilometers per hour, multiplied by the speed of Earth's gravity. Okay, what does that look like? Here's one from my gauge constant calculator spreadsheet using a track gauge of 1432 and a head width of 69.9. So let's go through the numbers again. So X 1432, head width 69.9 gives you an S, or the E, the distance between nominal centres, and that's the formula there in EN 13803, E over QV squared times G. G is gravity, 9.80665 meters per second, roughly. QV is your conversion factor, 3.6, that's meters per second, kilometers per hour. That's this number in here. Your E is 1502 or 1501.9 to be exact. So there's the equation in EN. 1501.9 divided by all of that gives you 11.82. And that's where the 11.82 comes from. And that holds good for 1432. If you change the gauge, if you go across the seas to somewhere like Melbourne or Ireland, even Northern Ireland, the gear track gauge is 1600. And if you're using a head width of 72 mil, which might be AS60 in Australia or UIC 60 over here, SEN 60 if you will, then your E value is 1672. Add the two together. Your conversion factor is still 3.6 kilometers an hour and meters per second. Gravity is still the same, and the equation is then 1672 divided by 3.6 squared, multiplied by 9.80665. And that, if you're in that gauge, 1600 gauge, gives you your constant value of 13.16 instead of 11.82. With me so far? I'm glad. So here's a question. If the required speed of a train is 80 kilometers an hour, and this is normally how we tackle the problem. Somebody says, I want the trains to go at this speed. And they've got to go around this curve. And that horizontal curve is 1,000 meter radius. What do you need to apply? In other words, the value of cant, if you wanted to achieve equilibrium. This is not what you would actually put down. This is the theoretical achieving of the equilibrium. Now, remember the formula? 11.82 speed squared divided by the radius. Step 2, there it is there, 11.82, 80 squared divided by 1,000. EQ is 76 millimeters. So if you wanted to travel around that curve at exactly 80 kilometers an hour, and the curve radius was exactly 1,000 meter radius, then if you raised one rail above the other by 76, the outer rail above the inner rail by 76, then you would travel round that curve in equilibrium. Your coffee cup would travel neither to the window on the left-hand side nor the window on the right-hand side. It would sit in the palm of your hand and you'd be able to drink it with no problem. But I hear you ask, wouldn't applying the equilibrium cant for the highest speed trains then overcompensate the centrifugal forces for the slower speed trains? Well, yeah, it would. So we apply some cant and we introduce some uncompensated super elevation, also known as cant deficiency, to reduce the risk of derailment and help steer the bogies around the curve. Because a little bit of cant deficiency helps that movement of the wheels on the curve. Remember the moving of the cones as they travel around? So passengers on high-speed trains might feel some centrifugal force outwards, and passengers on slower trains may even feel some force pulling inwards. But we're trying to strike a balance between trains travelling at 110 miles an hour, say, and freight trains travelling at 60 miles an hour. And trying to get the wear on the rails, the wear on the wheels kind of even. So cant deficiency, or D, is the equilibrium cant, EQ, minus E applied, whatever we apply. So how do we calculate the cant deficiency for a horizontal curve of radius 3,300 at 100 mile an hour, and we've got applied cant of 55. Oh, and by the way, we apply cant in steps of 5 millimeters. And that's because Gash couldn't count in anything less than multiples of 5. Step 1, use the formula, there it's again. Step 2, that's the numbers, 100 times 1.61934, getting miles per hour to kilometers an hour is 100 miles an hour times 1.61934. All of that squared, divided by the radius in meters. You see how I'm getting everything in the same units there? That gives you 55 plus D, which is my applied cant, plus whatever this unknown D is, as that number, which means that 55 plus D is, 93. And therefore, your cant deficiency is 93 minus 55. Your cant deficiency is 38. Now you can see the kind of ratio that you're getting there. You're getting 55 of cant and 38 of cant deficiency. And that's getting quite near the traditional way of applying cant and cant deficiency. There's a new science about that thinks that high cant deficiency curves are the bee's knees for controlling RCF. I'll differ. So how do we get the maximum speed? To get Vmax from that formula, we need to move it around about. So we've got an EA plus D, that's the applied of and the deficiency, equilibrium, is 11.82 times the speed squared divided by R. So we need to move that around about to take the Vmax out to one side. Now, I won't bore you with the steps. I'll show you the steps. So I've highlighted the number that's changing there in black. So I'm taking 11.82 over the step 1. I'm taking the R over and multiplying it. I'm taking the squared, change it to square root, dividing all that. The transpose formula, speed Vmax is the square root of E plus D divided by 11.82 times R. And that normal design rate of change for both EA and D is 35 millimeters per second. And that's done based on speed. Okay, here's another little question. On a section of existing track, if the horizontal curve has got a 600 meter radius and we've got 70 cant, what's the maximum speed to the nearest kilometre an hour that trains can travel on this section of track? And bear in mind that in the UK, our speeds are governed in increments of 5 miles an hour. I know that, but just for the purposes of getting this maximum speed out, let's work it in kilometres an hour. So we assume that the EA plus D is 70 plus 110 or 180. So we've got a D limit of 110. So we can't have any more D for normal cant deficiencies of 110. So we could run around there with D at 110 and an applied cant of 70. So our EA plus D could be 180, could be, and that would give us the fastest speed. It wouldn't be very comfortable, but there's the formula. There's the next step in it. Vmax equals all of that. And we round that one down and we say 95 kilometers an hour is the Vmax. Now, as I said, that wouldn't be a very comfortable ride because you've got a higher value of D than E. And D is normally less than EA. So your D is normally less than the cant you provide. When D is more than EA, it's called a high cant deficiency curve. And as I said, there are reasons for applying that. It apparently controls RCF better. Rolling contact fatigue cracks tend not to appear or don't appear to be so severe, because two things happen. You move the contact patch away from the running edge, and you also wear away the running edge, and you have a side wear problem, which is easier to manage than a rolling contact fatigue problem. So these days, high cant deficiency curves for certain curve radii can be applied, but you have to note them specially in your design. Now about vertical geometry. So vertical acceleration, we've talked about horizontal acceleration, is also limited by rules and standards. Passenger comfort is the main concern. Fairground ride geometry just isn't acceptable. If you want fairground ride geometry, you go to fairground. Big Dipper. The gradients are limited by traction capability to about 1 in 80. And the steepest UK mainline gradient is the Lickett Incline at Bromsgrove, just south of Birmingham. And that's a 1 in 37, or 2.703%. By comparison, if you're in Scotland and you're on the tunnel going out of Queen Street, you're in a 1 in 45, quite a steep climb going out of Queen Street, and quite a tricky braking point coming into Queen Street. And Beatwick Bank is 1 in 70, and the line up to East Kilbride is 1 in 60. So we do have steep gradients in Scotland, but the steepest one in the UK is at Lickett Incline. So the gradients are connected by, in railway terms, large radius vertical curves. And that limit, so the tightest vertical curve you can have, is 1,000 meter radius. And the other limit is the comfort, G-force. And that 1,000 meter radius limit, some people think 1,000 meter radius, well, that's not a very tight radius at all. It isn't. But in railway terms, it is. But let's just think about you and I, say, holding a string, and the string's 1,000 meters long, 1 kilometer long, and you go way over there 1 kilometer away, and we stretch the string tight, and you scribe an arc. You walk along and do 30 meters, and you pull a string, a pencil behind you, and draw that. That pencil line will look very straight. It won't look very curvy. It'll look very straight, because 1,000 meter radius isn't a very tight radius at all. And that's the tightest radius that we can connect gradients to in the UK. So how do we calculate gradients? It's dead simple. The level at L1 and the level at L2, and the distance between the two gives the gradient as a number. If you take the level difference divided by the length difference, or take the distance divided by the level and give the gradient as a ratio. There's an example. L1 84, so on, changes that, gives you level difference of 97 millimeters, distance of 70 meters. That gives you 97 divided by 70,000, that's the 70 meters in millimeters, times 100 over 1. That'll give you a percentage, that's 0.139%, or 70,000 divided by 97 is 1 in 722. But if you express the gradient in a 1 in, you need to then qualify it as rising or falling. When you do this one, if it's falling, it'll be minus. I mentioned the other limit, vertical acceleration. So gravitational force is your G-force that you feel. We limit these in vertical travel as a percentage of gravity. And that's speed in miles per hour divided by the radius in meters times 0.491. If your speed was in kilometers per hour, the 0.491 would be a different number. The design limit in the UK is 6% G, which isn't very much at all, 6%. And that's 0.589 meters per second per second. So an example of that, a vertical curve is 1,100 meters, line speed of 50, percent G is 50, square that, divided by 1,100 times 0.491, and the answer is 4.63% G. And that's a pass. It's within the design limit. Anything less than 6% G is a pass. Here's a question. Could the line speed in that example be increased from 50 to say 60 over that vertical curve radius of 1,100 meters? So can you get 60 mile an hour out of that? Here's the answer here. Here's your formula. %G, 60 squared divided by 1100 divided by 491. 3600 divided by 540.1. 6.67% G. It's a fail. So you can't get 60 miles an hour out of that. You could do 55 and it's only just a pass. It's starting to get uncomfortable. Okay, sprint to the finish. Design workshop. Okay, bringing it all together then. In this track design, the values in magenta boxes need to be calculated. The elements on the left-hand side of this, so the stuff in here, that's a bit of straight track. There's a transition. Here's a curve. The up line is red and the down line is blue. Why? I don't know. It just is. Okay. Oh, you can refer to the notes for this if you don't want to work it out now. Calculate the missing value circle. And here I've got a down line. We're looking for the applied cant. So we're told certain things about this. We know the radius, 1700. We know the D, 23. And we know the speed. What else do we need to know? There we go. So here's a little bit of hint. Go. KPH is MPH, then 1.619344. Oh, that number, in case anybody doesn't know, there are 1,609.344 meters in a mile. EA plus D, that's the formula, 11.82 times the speed squared in kilometers an hour divided by the radius. So you have to do a couple of things to get that to an answer that you can use to find out what E is. Here's a step-by-step then. Take it easy. 70 mile an hour times my magic number is 112.654 kilometers an hour. E plus D is 11.82 times that 112.654 squared divided by 1700. That gives me an E plus D equals 88. We know that D is 23, so E must be 88 minus 23 or 65 millimeters. And guess what? If you'd looked over there, you could have had a good go at that as well, because the speed's the same. The radius isn't a kick in the shirt off it. And I'm guessing that if that's 65, that'll be kind of around about 23. Shall we see? Okay, let's see if we can calculate the rate of change. The rates of change happen over speed and distances. So what do we need to know? We need a formula, and we need to be able to convert meters per second from miles per hour. So meters per second is a mile per hour times 1.61934 divided by, again, that 3.6. In this case, all of that equates to 31.293. And the rate of change is your applied cant, your EA, or your cant deficiency, if you're calculating cant deficiency, divided by the transition length. And the TL here, that transition spiral is 95 meters long, multiplied by the speed in meters per second. So we need to get that down into meters per second. And remember that the EA is 65 millimeters on that curve. Remember, that's up here. Okay, step by step, a bit more involved this time. Let's get it down to, seen that one before. And that's in meters per hour. So remember the kilometers an hour was 112.654 kilometers. That's 112,654 meters per hour. Dead simple so far. Divide that by 3,600, that's the seconds in an hour, and tells you that's 31.293 meters per second. The transition length is 95 meters long, and at that speed, where you're traveling 31.293 meters every second, it's going to take you 3.036 seconds to travel the 95 meters along the transition. So what have you got? You've got your rate of change is your 65 millimeters divided by 3.036 seconds, or 21 millimeters per second. And that one over there gives you a little bit of clue. That one was slightly higher because the transition length was shorter. See, that was a 95 meter transition. This was an 80. Okay, last one. Cant gradient 1 in something. Step by step for the cant gradient. Cant difference is 65 minus 0. We know it's 0 because the other bits are straight. The transition length is 80. If it's there, 80. Cant gradient is the length divided by the cant, and having the same. 0.065 metres is 65 mil, and it's 1 in 1231, or you can do it another way, keep it in millimetres, 80,000 millimetres is your 80 metres, keep your 65 as millimetres, it's still 1 in 1231. Okay, your turn for questions, and back over to you, Russell.
Excellent, Tommy. Thank you very much. That was very good. We've got a couple of questions to start with. So we've still got a lot of people on the call. If you have a question, the chat forum in the top right hand corner of the bubble, just pop your question into there, and I'll ask it the questions, and we'll get some feedback from Tom as we go. So Tom, the first question we have from Constantine was about the Hyperloop technology, and he's asking, do you think that Hyperloop technology will ever dwarf the current railway industry, or that some tech innovations like Horizon 2020 will protect it? Any thoughts at all on that as a wider industry question?
A very interesting question, and if you'd asked me to predict the questions I would have got tonight, I wouldn't have get that one unless I knew for sure that Constantine was going to be in the call. Hi Constantine, I hope you're doing well. Hyperloop technology, I'm not too au fait with it, but as far as I understand, it involves some kind of vacuum. But the expense of building it, I think if you were to bite the bullet and invest in it and build it, then it would be great for small numbers of people to travel very quickly from A to B. Whether it would ever catch on as a mass transit system, I don't know. And I don't know that getting your Amazon goods to you within the hour would be appreciated that much, or would justify the investment in that technology. I think any system moving people or goods from A to B has to be made, you have to make the financial case for. And I don't think Hyperloop technology stands up now, but I think in the future, it may do. So I'm not sure I'm answering the question, Constantine, but fair play for you for asking. I don't know.
Yeah, so I don't know much about Horizon 2020. I think is that something to do with shift to rail or something, or the European outlook on that. So I don't know, Constantine, if you've been involved in that yourself at all, in Horizon 2020 or anything.
Let's see if we can unmute Constantine.
Yeah, I'm going to try and find it.
Constantine.
Yes.
Me.
Go for it.
Yeah, so the Horizon 2020 is like an overarching project where there are European funded R&D projects which Network Rail is involved in. So they're looking at like implementing smarter technology for real-time data or analysis and stuff. And I asked the question mainly because of your detailed knowledge of the history of the railway. So I just thought, oh, do you think like Hyperloop is kind of what the next progression is for the railway in a way? That or maglev lifts.
I got quite excited about maglev technology when it first came out. I thought, well, this is going to be it, but it hasn't really taken off. It hasn't really caught on. Maglev, I know there are maglev systems and they're successful with what they are, but I think they're still very specialized, and it's like almost people showboating. We can do this, but I think in any technology, you've got to have something that works and something that is acceptable and something that is there's a financial case behind. I mean, imagine back in the days of the Victorians, they had the same thing. People were solving problems as they arose using empirical methods. They were more interested in getting safely from A to B than traveling fast. And that's part of the problem, is that the Victorian footprints that we're left with in the UK trying to fit modern high-speed railway systems on were generally designed for a 50-mile-an-hour steam railway. And we're asking trains to go use that same footprint and travel 140 miles an hour. And yes, we've got tilting train technology. So when somebody first thought, I know what we can do, we'll take the vehicles, and as it turns around the curve, we'll counteract some of that centrifugal force by putting some of that tilt on the vehicle. And then how did that work in real time? How could we tilt the vehicle? And they solved all those problems. And the Pendolino, I'm a great fan of the Pendolino. I used to travel on it a lot. And I find it a very comfortable way to travel, because you're traveling at speeds that you don't realize. And until you start to watch the horizon start to dip, and you realize that the train's banking itself into a curve at 140 miles an hour. And it's absolutely fantastic technology. And I think, if you make small advances in technology, then you'll take more people with you than concept. I mean, people are going to be offering rides to the moon soon. Yeah, okay, if you have enough money, you can book your flight now, and you can travel and do space travel in the future. But I think that'll be for a very select few of multi-billionaires. And actually, the masses here in the world will be more looking at autonomous vehicles to get them the first part of their journey to a train service, and then use the train service to get them a big long distance very fast. I think the advent of fast freight trains is upon us, and I was predicting fast freight as a work stream for the future 5 years ago, before Amazon was still thinking about drones and things. But actually, if you think about the amount of stuff that's now delivered by the DPD man that's just arrived at my house here at this time of night, you think, well, there is a demand for it. And the situation we're in at the moment, more and more people are turning to online shopping, and more stuff is being delivered in a brown parcel, and more blue wheelie bins are getting filled with the cardboard rubbish. So it's that progression is certainly there, but I think there's got to be a kind of groundswell of thing. And I think the original thing about Hyperloop would only catch on if the technology is proven, and I think the proving of the technology will be as good as its first catastrophe.
Yeah, that's fair enough. So
how many people
autonomous trains is going to be the next step first, isn't it then?
Yes. I meant to ask a question right at the very start of the presentation, which, if I can skip that, I'll go back to, I can do that, I can go back to the presentation again. And in this slide here, oh, that didn't change. Why did that not change? Oh well. I said from beginning, and it's supposed to go to my beginning slide. I didn't want to do it.
Okay. So it was a question about track basics or something, or track alignment
No,
basics?
it was on this slide here, so I wanted to put that particular slide. And I wanted to ask the question: does anybody know what's wrong with that track?
What's wrong with it?
There's no clips in it.
Correct. That's the thing that got me. So when I came across that, the first thing I thought was the track engineer's response. How is that managing to hold itself up there? There's no bloody clips in it. I was looking at it thinking, I never thought for a minute the shape, and I thought, well, that'd make a great turn back for Haymarket, platform 0. Yeah, I would send it back to 5 double quick time. But that was obviously a work of art, or that's what it was. It was in an outdoor gallery of modern art somewhere in downtown Sydney, I think, Manly Beach maybe. But I came across that and I thought that is, whoever had the patience to try and bend rails to that shape. As you know, bending rails the other way, sideways, is fairly easy. Mark Taylor and I could do it with well, maybe not Mark Taylor, but maybe me and Gash could do it with a bar.
Couple of Jim Crows on that, Tom, and get that sorted.
I know, but even Jim Crows, Mark, you would struggle to bend rails in that way. So I just, whoever
Adam Ferguson will sort you out for something like that.
I tried the best with a tamper one day, but never mind.
Right, we've got a couple more questions.
Right, okay.
Coming in here. Next one's from me, actually, Tom. As I was looking at the VTrans photograph, and you showed it going into it was a longitudinal underbridge deck type of thing, and I noticed there was sort of gabion style baskets, longitudinal baskets in the sort of cess area, creating what looked like it was supposed to be like a kind of ground beam, and it looked a pretty good idea. So just to see if you've ever kind of been involved in either specifying or in designing or actually installing any that type of solution. It's quite a...
I did get involved with it once, and I'm trying to remember where it was. It was somewhere on the route out of Waterloo.
Okay, yeah.
I can't remember the dive under, but the stiffness transition that was there.
There's a photo, yeah.
Yeah. So if I can say from current slide, oh, it does do current slide. So in the stiffness transition that I was involved in was a bit like this, but it actually had it was V-shaped. So it came to it narrowed this way and then went out there. So the stiffness was controlled laterally by graded ballast on either side, creating the stiffness or a stiffer track form, and you didn't have this big mitt that VTrans hadn't been invented.
Okay, yeah.
But I wasn't involved in the calculations, but somebody smart came up with the calculations that determined how stiff the sides had to be to provide additional stiffness on the vertical support.
So that was always a common run-on, run-off in structures, wasn't it? That the lateral flow of ballast, you would lose top because the ballast was wanting to migrate outwards, and that seems a pretty good potential solution for that. Yeah, I like that.
That's right. And the idea was that stiffness would be increased by the different width of unconsolidated ballast up to where it's held, and the gaping basket idea. And as it narrowed to a point at the structure, the containment of the ballast would make it stiffer and stiffer and stiffer, and actually provide you with a controlled stiffness transition from the ballasted track to the structure. That dive under begins with an A, and I can't remember it. It's annoying me. Acton. Maybe Acton. Anyway.
We've got a few more questions. So say if you want to pop a question in the chat forum, we'll get through them. Next one's from Andy Batters. Andy said he's not a PWI designer. However, an old colleague once told me that a twist fault will always derail a train regardless of speed. You have said that transitions are 25 millimeters a second, ones we're talking about. So my question is, what's the difference between an acceptable transition and a twist fault? Good question. Yeah.
So transitions are the part of the spiral where we apply the cant. So our cant gradient, or our twist value, is limited at 1 in 500. So that's 1 millimeter for every 500 millimeters you go along the track. A twist fault that you would need to do something with is something less than 1 in 200. So when we're designing our transitions, which have the change in cant, we're actually designing a twist. But our design twist is kept at a gradient of no steeper than 1 in 500. When you get to twist faults that will derail trains, so you're talking about twist faults less than, say, 1 in 100, and the nearer you get, the lower you go, the more likelihood you have of a derailment. Twist faults will always derail. That's never a truer statement than the one you related. Twist faults will derail a train irrespective of speed. The only thing the speed component does in a twist fault is determine how much carnage there is once the train's off. So if you derail on a twist fault at slow speed, bump, bump, stop. Oh, the tamper's fallen off again. Okay, that kind of thing. Or if you're in a pendulum and you derail on a twist fault, you'll have people and body bags and all sorts of mess to clean up. So the twist fault will create the derailment. The speed will create the aftermath. So that's why twist faults, in terms of the track technology, we need to control twist and our influence on twist, where we have designed twist in our transitions spirals, where we apply the cant from straight to curve, is kept at 1 in 500. And that's to make sure that we don't stray into the territory where, as soon as that starts to go off, maybe during construction tolerances or during the track degradation in service, we don't stray into that steeper than 1 in 200 and, God forbid, steeper than 1 in 100, and we actually start to encourage twist.
Okay.
Hope that answered the question.
Okay, sounds good. Yeah. We have another question from Stuart Corey, who is asking, you've described working out the speed of a specified alignment and touched on limiting radii for speeds. The track designer also needs to place that geometry. Do you have any processes or tips and tricks for doing that?
Well, maybe I can demonstrate something if I can get out of this, right? So if I pull up this here, so this is a little crib sheet, right? Can you see that okay, Russell?
Yeah, perfect. Thanks.
Yeah, okay. So what we got here, we've got, this is just an Excel spreadsheet. There's a formula in there. There's a formula here that work all these things. All these formulas, the formula you've seen tonight for rate of gain of cant deficiency, cant gradient, okay, with some error trapping in there. So the figures in blue are the ones we can play around with. So let's say that this particular element, 713 meters long, it's running 50 mile an hour at the moment. The curve radius is what the Victorians gave us. It's 457. We can't normally play around too much with that. In terms of playing tunes on the curve radius, you play around a bit. But actually, you've got a fence line either side of you, boundary, some sort of constraint that you can't really change the radius very much. So you can play around with the applied cant and you can play around with the speed. So let's play around with the speed. Let's say we want to see, can we go faster than that? So can I do 55? Well, let's go 60 miles an hour. So if I type 60 in there, you see some of the figures start to change straight away. Now I'm getting red error messages, which tell me, oh, it's bad. You need to do something about that, Tom. The very first one I'm going to tackle here is this 151 deficiency of cant. Now, I talked about 110 being the normal value. 150 is the absolute maximum. So the minute you breach 150, computer says no. And there's another one in there where D is more than the applied cant plus 50. That brings up a yes as well. That's also bad news. Other things that are happening with that increase in speed is I've breached the 35 millimeters per second limit, normal limit, on rate of gain of cant deficiency. I've done the same down here. So that's telling me I've got too much cant deficiency. Well, that's dead easy to do. I can up the existing cant. I can increase the super elevation that's on the track from 90 to something a bit happier. So let's go whole hog. Let's make it 150. That's the maximum I can apply in the UK. And that immediately takes the rate of gain of cant deficiency down, but it's put the rate of change of cant up. And again, I've breached the 35 millimeters a second, and those have gone amber. I'm also getting down near my 1 in 500 limit here. So my twist value that's happening as I apply that 150 millimeters over the transition length of 90 is starting to get dodgy. Okay, so let's go back to this figure again. I'm still trying to keep this 60 mile an hour. I'm thinking, okay, let's knock the cant down a bit. I'll do 140. Cant gradient's better. Rate of change of cant's getting there. Still a bit too steep on one side. Let's try 135. Oh, liking that on the first transition. So that transition's all sorted. But this one isn't, because I'm going from whatever that element is, going from a straight. So this transition, 135, going down to this straight, is not working in here. So I'm going to do 130. And now I've got D just above E. And I think 135, I can live with that. And I need to sell it to the track ram. So because I've gone beyond my normal rate of my normal design limit, but I haven't exceeded my exceptional, which is 55 millimeters a second, I can say, actually, I can increase the speed of trains around that curve from 50 up to 60 mile an hour, and that may shave 2 or 3 seconds, and you can calculate the whole thing. But on that one element, there I've got a 10 mile an hour increase. And that's quite a prize in track design. I haven't changed the radius of the curve. I've just put the cant up a bit. Now, can I get 65? Oh, sorry, not 656, 65. And again, I could just about squeeze 65 miles an hour out of that because I don't have any red figures yet. Everything's still amber, so it means I need to sell it to the track ram and get some kind of sign off because this is starting to get uncomfortable. I've got high values of cant deficiency, and slower trains will be experiencing negative cant deficiency and excess cant, and these are not good things, and that's just wearing away the rails. If I tried to get 70 miles an hour out of it, immediately my E plus D goes up above 300, and the most you can apply in these two values is 150 either side, and that's the absolute max. But again, with 193 of deficiency, you're getting rates of gain of cant deficiency on this that are way above normal. Okay, so that's a tool that we use to optioneer and change what we had. I can't remember what that cant was. Wasn't 50, it's probably about 80. No, it was 90, I remember. There you go. So that's how that one was. And that element is sitting there today, and that's the element somewhere between somewhere and somewhere else. I meant to ask, did anybody get the station name right, Russell?
I don't think so. I don't think it was career, certainly. So if we have anyone that knows the answer on the call still yet, it looks
Hands
very
sorry about the quality of the photograph, but it came from a cab ride video, obviously, because sitting on the 6-foot rail here. Well, that's Giffnock Station on the East Kilbride branch, about to be electrified or soon to be electrified.
Absolutely, yeah. So thanks for the answer for that one. I hope that answers your question, Stuart. The next one was about myself, and just about the 2-second rule, the infamous 2-second rule. And I don't know if you were able to kind of explain that very briefly, Tom, about does that involve sort of minimum elements? It was a kind of a restriction you always used to. Is it a kind of rule still, or is it a kind of guidance for the practice?
It's definitely a rule, and I was talking to Liam Jackson just by coincidence today of Network Rail fame about a standards challenge that I raised last year on ballast ramps.
Okay.
And I'll digress to ballast ramps first just to cover that one off. The ballast ramp rule, which says the ballast ramp shall be created, which will be line speed divided by 6. Right. Well, there's an empirical value plucked directly out of midair. Right, there you go, a paduma. So ballast ramp line speed by 6. And I say, okay, well, that's fine. But on shorter things, track off jobs, bridge jobs, 20-meter bridge, 90 mile an hour track, you've got ballast ramps, 17 meters either side of that, but longer than the bridge itself. So your track disturbance is more than 100% more than what you were originally going to do. Surely we should in the UK save a lot of money if you cut 20, 30, 40 meters off every track renewal you do by not having the requirement to do ballast ramps. And anyway, you can't make them effectively. If anybody at the call has ever made an effective ballast ramp without churning up the track when the dozer turns round, and then Joe blogs on the dozer backblading it by eye, please let me know, because I've yet to see a decent ballast ramp created. And all you get is a 50-50 mix of ballast that's neither consolidated nor the ideal transition that some geotechnical engineer's got in his mind's eye. But the 2-second rule. So I mentioned the 2-second rule to Liam today, and I said he was talking about the tracker, and they use the Network Rail tracker to see what standards have been challenged the most and which ones they need to look at to see if there is a reason for change of Network Rail standards. So this is the 2-second rule is a Network Rail standard. It's not a railway group standard. It's not a legal requirement. So it's just something that Network Rail has. And the idea is that the 2-second rule is to do with people's comfort. People don't like being moved around by moving from one geometric element to another every 2 seconds or so. And it sets up an oscillation in the vehicle bogies, which is the waveform tends to excite the vehicles, and the vehicle can't get out of that rhythm. So that 2-second or 2 hertz rule is why we try and keep elements longer than that. And if you think about it, if you've got elements that don't meet the 2-second rule in your design, you've got lots of fussy design. And as a track designer, you're trying to achieve the longest elements that you could possibly give so that you have a simple track alignment. Simple track alignment run and are maintained easily. They run good easy to maintain, and you will keep them forever because they are simple. Once track gets to if track's convoluted in its design, then it'll never run great, and it'll be a bit of a pain to try and maintain. I know it's easier these days with Tamper's computer controlled and all done by onboard geometry control files, but if you have simple elements and long elements, then you'll keep them better than lots of little 2-second elements. And I guess that's me going from good design, the difference between good design and compliant design. In this picture here, I could have had 2-second elements all the way from the overbridges at this side of the station to the station and all the other side. It would have been compliant with the requirements of the standard. However, it would have been a very fussy design. So as a designer, I'm trying to combine elements where I can. I'm trying to see what the average curve radius is. And in fact, that's what the design software looks at when it does regression. It looks at the various radii that have been surveyed, and it tries to pull a single radius out of there, which is an arithmetic average of all the radii together over that given length. And hopefully that will be able to be installed with the minimum of track slews and lifts. Okay. So I've answered the question about 2-second rule. The 2-second rule is there because it's comfortable. If you keep elements longer than 2 seconds, you're not constantly changing direction. It helps the vehicles, their oscillation, because their natural frequency is that 2 Hertz thing. And it also makes the designs easier to maintain and go from compliant design to good design.
Sure, okay. Brilliant, Tom. A few more questions quickly. One from Michelle. Hi, Michelle, how are you doing? Michelle was asking about track stiffness and the influence of kind of platform walls. You know, we talked earlier about the run-on and run-off structures and gabions at the side, what effect that has, and any thoughts on the effect on platform walls because we don't make any formal allowance for that, but any experience of that, Tom, at all, or impact
as a maintainer,
of platform walls?
Only as a maintainer, and I'm talking about maybe if I was a maintainer in this one. So that picture there at Giffnock, you notice there's at least 2 different track forms in there. You'll see on the upline here, there's a solid riser wall, and then there's harp units. So that solid riser wall was the original platform, and then it was extended with harp units, and you've got a difference in ballast width here, and that creates a difference in stiffness, especially on the low rail. And I know as a maintainer, when you come across that kind of thing, you'll notice that if the top is going to go off, if you're going to require treatment to track top, you'll probably require more treatment in this area here, where there was a wider space or an uneven space than you will in here, where you've got the solid confinement of the platform riser wall, especially on curved track. And that is an influence that's there. Regular tamping solves it, but if you're going to have track fault problems, or repeat track fault problems, I would look at other influences and think, okay, do I have a change in, why have I only got problems in that half of the platform? Why is it only this end of Giffnock Station that's giving me the issues? Well, that's where the platform riser wall changes on the side. So maybe that's giving me a change in stiffness.
Tom, do you think lateral resistance plates in the forefoot in the area of the cross walls would help?
I'm not sure that it's a lateral problem. I think that the stiffness is more related to the top going off, the cant going off, twist fault starting to occur.
Well, it's effectively sort of like ballast migrating, if you like.
Yeah, well, if you think about as the ballast loads, right? The ballast, it loads vertically. It's also got some sort of lateral loading at the same time, and obviously the ballast crystals are stuck together, long faces together. But on the harp units on this side, there's more resilience here because they've got more room to move than they have in here where they're confined. So this track here will be a little bit stiffer than this track here. And what that will give you is perhaps, and it's not a guaranteed thing, it would be a different stiffness and maybe a different top quality in this part of the platform. These sections are typically small, they're platform extensions that have been done like that, but there may be other areas where you've got a rock cutting and you actually, the depth of the rock cutting is actually constraining the ballast and allowing it not enough room to move sideways, and it becomes a little bit stiffer in there. I don't know if it would affect the track that much, but there will be a measurable difference in stiffness. It's the impact that it has on track. So if you've got continual top faults in one area, and you think, well, why do I only get them there? I don't get them elsewhere. You might want to look at, it's in the station platform at Giffnock, and it's only at the East Kilbride end, and that means, I can attribute it to the HARP units. But as I said, fixing that problem would then need an approach to the structures engineer to rebuild the station riser wall as a solid unit, or tear the whole platform down and replace it with a polystyrene unit, which they might be doing at Giffnock.
Absolutely. I hope that answers the question, Michelle. There was another little comment from Stuart Corey, and he was talking about if travelling on the first one or two coaches of a Pendolino. He says you can feel 4 kicks, one at the start of the transition, one at the start of the tilt, one's at the end of the transition, and one when the tilt reaches the tilt system reaches equilibrium for the curve. So I don't know if you've ever experienced that, Tom, at all, or a Pendolino.
Well, as you know, travelling first class in the Pendolino, as I do, Russell, I tend to be smashed most of the time. No, I do travel on the front coach of the Pendolino is a little short coach because it's normally got catering on it too. But that and the Voyagers, you do feel them, and that's just the lag. So the system isn't reading the track ahead; it's reading the track beneath itself. Okay, and there is a little lag as the system detects that it's on a transition, going on a curve, or coming off a transition, going on the straight, and it's trying to adjust very quickly the inclination of the carriage correctly.
Yep.
So I'm not really too sure about the smarts involved in that, but obviously there's microprocessors involved, computational power, but eventually at the end of all that, there's the hydraulics that push the coach over, that tilt the coach, and it has to tilt it to the right value for the curve to get to that kind of equilibrium.
Sure.
And it doesn't actually achieve equilibrium, it achieves something the same as the ride quality in a normal train. So you still get some centrifugal effects, but not the same centrifugal effects you would get if the tilt mechanism suddenly stopped working and the train was still trying to travel around that curve at that speed. You would definitely feel uncomfortable, and you would definitely lose control of your wine glass as it slid up the table quietly.
Sure. Okay. A final comment from Gash's Laddie about ballast ramps and 2-second rules. Good healthy canteen chat for standards, I think. So yeah, absolutely. It's one of them brought up by myself, in fact both of them. So yeah, but it's these type of things I think you do miss, though, in the not seeing people for 12 months, etc. Talking about the smaller things in life that are equally sometimes less important. But
what was interesting when Liam was telling me about the standards challenges, he said, strange enough, that tracker thing they use, he said we don't get too many applications to deviate or have a derogation against the ballast ramp part of the standard. And I said, well, that's quite simple, because from a designer's perspective, it's no skin off my nose. I'll show 2-second ballast ramp. There you go, bing, bang, bosh. Costs me no extra effort. The extra effort is on the guy that's out there, the technician on the Saturday night, who's to make the bloody thing.
Yeah.
So that technician is then forced with creating a 17-metre ballast ramp either side of his excavation. And the only tools he has to do that is a dozer that's got to spin round about at least once, probably twice, churn up the ballast, and then try and backblade something that is very ordinary and doesn't get consolidated. And at very best, it's 17 metres of dirty ballast as a wedge shape with nice clean pink ballast on the top of it, and it gets somehow that's supposed to be a transition. But when Liam was explaining how these things get challenged in the standard, he said there was a big discussion about the ballast ramps, and everybody's in two minds about it. But the geotechnical engineers won the day because they said, no, we need this transition, because if we don't have that as a standard, it's then like open. There's nothing, no rule anyway. So in terms of, would we rather have a standard that says ballast ramp or nothing? They would rather have the ballast ramp standard. And I put it to them that actually what they should have is a standard that says, thou shalt consolidate the subgrade, thou shalt lay your fine separate or whatever else you're laying, and then you shall compact your ballast in layers up to sleeper soffit -10. And that's the way I used to do it. And I don't see why everybody can't adopt that and forget ballast ramps. But it will remain canteen chat unless more people start challenging that standard. But by the time ballast ramps get to the making of them, it's too late to challenge, because it's the designer that puts them in to comply with the standard, and it's the guy on the site, the technician on the site who's got to build them, that is the one that's cussing it.
Yeah, good point.
And he's got no room. He's just got to make it because it's on the design. He's building the design. The designer's got no initiative. I only took the initiative to challenge that standard because I wanted to save the rail industry a bob or two.
Yeah, which isn't a bad thing. Absolutely.
I thought that's what it was all about, Russell, but it got knocked back. Anyway, I've just got to swallow my humble pie now.
A final one from Constantine, just thanking you for the presentation, Tom, and the chat as well. So, and we've got one more just popped in by Michelle. Should this not be challenged by a PD?
Principal designer.
Right, thanks, Michelle. Just keep me right with acronym there. Are we talking about the ballast ramps, Michelle, or the
ballast ramp? Surely that is a classic principal designer challenge then. The practicalities of installation.
I raised them all, Michelle, in my standards challenge 72 was full and detailed in its explanation of why it was impossible to create effective ballast ramps and how they were ineffective, blah, 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 the whole thing, chapter and verse, and how much money could be saved. And it's been discussed at Network Rail. So the panel got together, Network Rail discussed it, discussed the merits of my challenge, and decided my challenge must fail. What Liam says is it's not going to go away. It's still in his mindfulness list. So he's going to keep it in mind the next time. But he is kind of, until people start to challenge it through the tracker, Network Rail don't have a lot of evidence of it, other than my properly raised through the channels standards challenge.
Okay, I shall maybe join you in that challenge then.
Shall I forward it to you, Michelle? I'll let you see what I said.
Yes, if it means starting a fight, I like that.
Well, that's what I thought. I thought nothing ventured, nothing gained. I didn't get one arm, blah, blah, blah.
For the benefit of the audience, we don't condone violence in here, so. Well done, Michelle.
Healthy
that sounds
debate.
Like it's healthy debate.
Sorry,
yeah,
it's not the Glasgow section anymore. Violence isn't allowed. Okay.
Great. Brilliant. Thanks very much, Michelle. That's great. I think, let's see, I think that's all our questions, Tom, which you've done brilliant making your way through. If I could, I'll just finish off with a quick vote of thanks, if that's okay. We had a kind of record attendance tonight of 45, I think at one stage I counted, which is a brilliant attendance, and it just shows the amount of interest in both yourself and the subject matter tonight, which you've managed to get together. It's fantastic. You started off with this early history of the tracks, and you said that wide gauge has always been an issue, and I think it always has been, always will be. And the early stone blocks that you showed early on, I think I remember seeing, albeit a concrete maybe version of that or something, in the Dalmeny sidings. There's a few examples around the country, but I suppose even we do use that similar kind of design to a modern twin block sleeper and high speed rails in Europe and everything. So it's, although it's very old, some of the principles are still apparent, you know, in the industry nowadays. And one of the key points I picked out about, you know, the replacement of components and actually being able to replace them as singular components, you know, in a practical means was pretty important. It's very easy just to, when you need a new set of tyres, just get a brand new car, but actually does that make any sense? And that's what we sometimes get forced into the railway, because we can't particularly replace certain elements of that. So trying to think about that as we design things and build things is a good thing. We played a little bit of acronym bingo with some of the track design terminologies. That was good. And that kind of explanation about the 11.82 constant C number on the 1432 gauge, I had to kind of rack my brain about the 11.82. I think I remember reading it quite many years ago, but thanks for the useful reminder on that as well. And the practical sort of examples, an important reminder, but always keep the same units. Very easy to get kind of mixed up with miles per hour and meters at the same time, and then the calculations go horribly wrong. So that really important reminder. And I think the main thing out of tonight for me, as well as the history of how we got there, was the facts and information, the formulas behind what we have now. So we have some pretty exciting pieces of software, whether that be a pretty simple Excel spreadsheet, or indeed something a bit more complicated that you can throw some numbers in and get the answer you want back from that. But actually, you know, trying to better understand how that comes about, it makes it much easier for the kind of designer to establish, you know, how he's trying to get that the final answer to suit. So it's been an excellent presentation, Tom. Thank you very much on behalf of the Edinburgh section and the rest of the PWI members and guests tonight. And I would ask if everyone could unmute their microphone, and we'll try and give Tom a suitably warm round of applause to thank him for tonight. Well done, Tom. Thanks.
Tom, if you're looking to take over from Jerry Toner, you're going to have to take it down a couple of baritones.
No. I could never overtake the great Jerry Toner.
Absolutely. I don't think we could convey the language on the channel tonight as well, so it might not be quite appropriate. But well said, Mark. Well said. Just before we finish for the night, just a quick reminder of our next Edinburgh meeting, and it'll be again on a virtual format, like tonight's, and it's Wednesday the 5th of May, and we have two speakers. Paul Finney, the director of a company called Swix, who's providing a presentation on predictive maintenance at S&C. And also, in addition to that, John Edgley, the president of the PWI, is coming up or will be virtually joining us in Scotland anyway, and giving us the Scottish section's presidential address, in addition to his presentation on industry competencies recognition. So what within the industry and indeed Network Rail looking at from an industry competence point of view moving forward. So a kind of double presentation next month. So thanks again to Tom for an excellent presentation. Thanks for the rest of the audience as well for joining us tonight, and I hope you have a good remaining evening, and hope to see you all in the future for some more presentations. And thanks again, Tom. Cheers.
Thanks, Tom. Thank you.
Thank you all. Bye for now.
Cheers.